I welcome you all for this lecture series on deep learning. In this lecture, I will briefly discuss about performance metrics in deep learning. The performance metrics are numerical measures used to evaluate how well it is a numerical measures used to evaluate how well a deep learning model works on unseen data rather than only on training samples. They help us understand whether the model is accurate, reliable, and suitable for real world deployment. Different matrices are used for classification and regression problems because each type of task requires different ways of measuring errors and correctness. These metrics guide researchers in comparing models, tuning hyperparameters, and selecting the best architecture. Next, the accuracy. Accuracy measures the overall correctness of the model by calculating the proportion of total predictions that are correct. It is computed as the number of correct predictions divided by the total number of samples. Accuracy is most useful when the data set is balanced, meaning all classes have roughly equal samples. However, in imbalanced data sets, accuracy can be misleading because a model may predict the majority class most of the time and still achieve high accuracy. And accuracy is given by true positive plus true negative divided by true positive plus true negative plus false positive plus false negative, and is best suited when data set is balanced. Next metrics is the performance evaluation is the precision. Precision measures how many of the predicted positive cases are actually correct. It has been given by the formula true positive divided by true positive plus false positive. It focuses on the reliability of past predictions and is calculated as true positive divided by the sum of true positive plus false positives. Precision becomes very important in applications where false alarms are costly, such as spam filtering, fraud detection, or disease diagnosis, where unnecessary treatment must be avoided. High precision means a model rarely label negative cases as positive. So it is important when false positives are costly. Next, recall. Another name is the sensitivity. Recall measures how many actual positive cases are correctly detected by the model. It is computed as true positive divided by sum of true positive plus false negatives. There, in the previous case, false positive, here false negative. This you must remember. Recall is critical in safety sensitive domains such as cancer detection, fault monitoring, or sensitive security systems where misleading a true positive can serious consequences. A model with high recall ensures that model most real positive cases are captured. Next measure is F1 score. F1 score is a harmonic mean of precision and recall and provides a single measure that balances both. It is especially useful when the data set is imbalanced, when we need both false positive and low false negatives. Because it analyzes extreme difference between precision and recall, F1 score gives a more realistic measure of model performance than accuracy alone in many real world classification. So F1 score is being given by 2 into precision into recall divided by precision plus recall. It is also useful for imbalanced data sets. Next one is ROC curve and AUC. ROC curve is a graphical representation that plots the true positive rate against the false positive rate at different classification thresholds. It shows how well a model separates two classes. The area under the curve AUC summarizes this performance into a single number between 0 and 1. A value near 1 indicates excellent classification ability, and zero point 0.5 represents random guessing. And ROC AUC is widely used in compare classification independent of threshold selections. It is used for better model performances. The next metric is the regression matrix. It is used for mainly continuous outputs. For regression problem, where outputs are numerical values rather than classes, different error based metrics are used. This include MEE, mean absolute error, mean square error, MSE, RMSE, root mean squared error, and R square score. It is used for goodness fit. Each metric measures prediction error in a different way, helping researchers understand whether predictions are consistently close to the actual value, whether a large error exists, and how well the model fits the data trend. These metrics are essential in applications such as price prediction, weather forecasting, and signal estimation. Next one is the confusion matrix. As I've said, the confusion matrix is a table used to evaluate classification performance by comparing predicted labels with actual labels. It contains four components: true positive, false negative, false positive, and false negatives. From these values, all other metrics such as accuracy, precision, recall, and F1 score can be calculated. The table will be like this. The confusion matrix provide deeper insight into the type of errors and models make rather than giving only a single performance value. Actual positive, actual negative, predicted positive, predicted negative. By making use of this, we can able to calculate these values. The total samples been taken it as 40 plus 10, 50, 55 plus 45, 100. 100 samples have been taken. From this, we can able to measure recall, precision, and F1 score. We can able to calculate it. Next one is the accuracy. The accuracy measures overall correctness of the model. In the given example, the model achieves the how achieves the 85 percentage true. So accuracy is being given by the formula true positive plus true negative divided by all values we have to taken into account in the table. True positive, true negative, false positive. So the total sample value is 100. And what is the formula for accuracy? True positive plus false negative. True positive plus true negative. We are going to take what is the true positive value? The true positive value is 45. True negative is 40 plus 45 divided by 100, 0.85. So the percentage is 85 percentage. We are getting the accuracy is the 85 percentage out of total. What is the sample? 100. This indicates that the model performs well overall, but this number alone does not tell us how well it defines positives or negatives separately. Therefore, other metrics must also be considered for a complete evaluation. Next, precision. Example, interpretation. The precision measures this example precision value. We are calculating it as 88. This is given by the formula true positive divided by true positive plus false positive. We know true positive value from the table. True positive is 40 and false positive value true positive 40 plus false positive 5. So we are getting 80 0.88. The precision percentage of percentage in is 88.8, means that out of all predicted positive cases nearly 89, approximately 89 percentage are correct. This shows that the model's positive predictions are reliable and it produces relatively fewer false alarm. Such performance is desirable in systems where incorrect positive data predictions are expensive or risky. Next example is the recall, the sensitivity. And the recall of here we are calculating it as true positive divided by true positive. Here they false positive in the previous case, here false negative. So we are calculating 8.8 and the percentage is 80%. The recall of 80% indicates that the model successfully identify 80% of the recall positive cases. This suggests that some of positive samples are still mislead, but the majority are deducted. Depending on the application, improving recall may be necessary, especially in medical or safety critical tasks. Next, F1 score. It has been given by the formula precision and recall. 2 into precision and recall divided by precision plus recall. So already we found out the precision value is 0.88, recall value is 0.8. If you are substituting, we are getting 0.84. The F1 score 84% shows that the model maintains a good balance between precision and recall. It because here the pre-call we got 88 percentage, recall we got 80 percentage. So it is maintaining 80 between 88 percentage and 80 percentage. So 84 percentage shows that the model maintains a good balance between precision and recall. It confirms that a classifier is neither producing too many false positive or nor missing too many true positive. This makes the model necessary reliable for imbalanced classification tasks. The next measure is the ROC curve and AUC. the interpretation. The ROC curve is the example shows how classification performance changes with the threshold value. While AUC value is 0.92 means indicates excellent discrimination ability. This means here it indicates this means the model can clearly distinguish between positive and negative classes most of the time, making it suitable for real world deployment. And regression model, regression metrics. Next one is the regression metrics. I have told you the regression matrix is used for the continuous data 100, 150 to 200. Predicted, we have been given it as 110, 140, 190. Error is being given between 10, 10, 10. This is the example. From this, we have to find out. In the example with actual values 100, 150, 200 predicted and 110, 140, 120, 190. Each prediction has error of 10 units. This shows that the model predictions are consistently close to actual value. See here, 100 it is nearer to 110, 150 it is nearer to 140, and here there is 110 it is nearer to 100, 140 is nearer to 150, 190 it is nearer to 200. This shows that the model predictions are consistently close to actual values. Using MAE, MSC, and RMSC helps quantify how large these errors are, while R square tells us how well the prediction follow the true trend of the data. First, from this data, we are able to calculate mean absolute error MAE. MAE is given by mod of 10 plus 10 plus 10 divided by 3. So 30 divided by 10, 10. Mean square error, the average of squared predictions, squared prediction, mod of 10 plus mod of 10, mod of 10. Because errors are squared, large mistakes are penalized more heavily. This makes MSC useful. That is, so between actual predicted value, it gives simple and interpretable measures of prediction errors in the same units as the data. Lower MAE means better prediction accuracy. It is less sensitive to large outliers compared to square errors. Next, mean square error. See here, 10 square plus 10 square plus 10 square divided by 30. We are getting 300 divided by 300. We are getting 100 because errors are squared. Large mistakes are being calculated. This makes MSC useful when large errors are particularly undesirable, such as financial predictions or control systems. A smaller MSC indicates a more accurate regression model. Next, root mean square error. Square root of MSC. Here, what we are getting 100. So, squared root of 100, the value is 10. MSC and it represents the prediction error in the same units as the largest target value. It is widely used because it is easier to interpret than MSC while still penalizing large errors. Lower RMSC values indicates that models predictions are closer to the actual value. Next, R square score. It has been given by measures how well the model fits the actual data. It ranges between 0 and 1, where values is closer to 1 indicates better fit. And higher R square means that model explains most of the variability in data. That is showing that the predictions follow the actual trend closely. It is commonly used to evaluate regression models quality. Next, coming into the conclusion, the performance metrics are essential because they help evaluate classification models, analyze error types using confusion matrix and it measures the regression accuracy and selects the best model for deployment. Without these metrics, it would be impossible to judge whether a deep learning model is reliable, accurate, or suitable for real world applications. So they ensure that model generalizes well and perform consistently on unseen data. Hope everyone understood about the problems, the what is meant by confusion matrix. From that, how we are finding out accuracy, recall, precision, F1 score, and what is ROC. And from the given data, how we are able to calculate MAE, MSC, and RMSC. So these are all the things about the performance metrics in deep learning. The remaining things we'll discuss in detail in the next lecture. Thank you.